Hey guys, Mr. Betts here. We're going to continue talking about finding volumes using definite integrals. So if you remember in the last couple of sections, we were looking at finding volumes by using areas of cross sections. And we're still going to be using that idea, but we're going to be using that idea with some specific types of problems. So the next few sections, starting with this one, we're going to be looking at what kind of shapes we're going to get if we revolve a function around an axis. So the idea here is maybe we were building something, and that something could be, say, the nose cone of a plane. And to get the nose cone, to get that shape, we're going to take the square root function and we're going to rotate it around the x-axis. All right, so we take this two-dimensional function and we rotate it around the x-axis and give us a three-dimensional shape. So it might look something like this. So let's kind of look through how we're going to get that shape and then how we can use what we know about it to find the volume. All right, so first of all, we're going to take the square root function and rotate it around. So just kind of giving you a visual here of how we're getting the shape. So we have this nose cone. It doesn't have to be a nose cone, but it's a shape that we're getting by revolving around an x-axis or an axis, not necessarily the x-axis. So what we want to do here is go back to how we originally started finding areas. So the way we started finding areas is we broke an area up into rectangles. So we used these Riemann sum rectangles. We found the area of the rectangles using the width, which we call delta x, and the height of the rectangle, which was represented by the value of the function. And to find the area of the rectangle, then we multiply width times height. And if we then accumulate all of those areas, so we add up or sum all those areas and use more and more rectangles, we can use a limiting process that turns into a definite integral for an area. Well, now what we're going to do is we're going to take a Riemann sum rectangle, just like we did before, but then we're going to look at what the volume we get, what that volume is going to be if we revolve that rectangle around the axis. So just another visual here, if we take a rectangle and revolve it around an axis, what we end up getting is a disk. So what we're using here is called the disk method. So this disk is something that we can find the volume of. So to find the volume of this disk, it's actually a cylinder. So the volume of a cylinder is going to be the area of the circle times the height, or in this case, the thickness of the cylinder. So that's going to be pi r squared for the area of the circle times the thickness, which is going to be our delta x, and we're going to add up a bunch of these areas. So the idea is we're slicing it up into small sections, but instead of adding up areas of rectangles, now we're going to be adding up volumes of disks. So let's look specifically at how we're going to find the volume of a particular slice or cross section. So to find the volume of a cylinder, we're going to take the area of the circle. So the volume of this particular cylinder is going to be pi r squared, and then we're going to multiply it by the height or the thickness of the cylinder. So the thickness here is pretty easy. That's just going to be delta x. So this is going to be pi times the radius squared times delta x. And then the radius we can actually get by using the value of the function. So this f of x here, in this case the square root function, is giving us the value of the radius. Now it's giving us the value of the radius because we're revolving around the x-axis. So the radius is essentially going to be the distance between the axis of revolution, which in this case is the x-axis, and the function that we're revolving. So that distance in this case is just the value of the function. So the radius is f of x, and so since that's the radius, we're going to square that. So the volume of this particular cylinder is going to be given by pi times the function squared times delta x. Now, if you imagine what's going to happen if we add a bunch of these volumes together, we can get the volume of the whole thing. So again, kind of looking at this more generally here, if we're trying to find the volume of what we would get if we take this function and revolve it around the x-axis, what we're going to get is slices that were Riemann sum rectangles before, but now these slices are going to become cylinders. So we can find the volume of a single cylinder by using that volume formula, and then summing them all up and making them thinner and thinner and thinner, we're going to turn that into an integral. So where the volume of one slice is pi times the function squared times delta x, as we use more and more of them, delta x is going to approach dx, and so our volume is going to be the integral of that cross-sectional area, pi r squared, and r is going to be given by the function. Now, I'm going to write this a little bit more generally here. First of all, let me add in my limits. And I'm going to put r of x here, because in some situations, if we're revolving around a horizontal axis, but it's not the x-axis, then we can find that radius as a function of x, but it's not necessarily going to be the function itself. If we are revolving around the x-axis, though, that radius is just going to be the function. So that gives us a formula that comes from this formula that we've been using before, but the area, the cross-sectional area, is going to be the area of a circle, so that's going to be pi r squared. Notice that in this version of the formula, the pi is out in front of the integral. The constant multiple rule for integrals says that we can do that, and so we have the area of the cross-section times the width of the cross-section gives us the volume of a single cross-section, and then our integral accumulates all of those volumes into the volume of the entire solid. Now, one other thing I want to mention is that we can also do this with respect to y. So rather than revolving around the x-axis, which is going to give us an integral with respect to x, we can slice this up horizontally. And let's say this is an a value and a b value here. So we can revolve around the y-axis, which would give us maybe some vase-looking shape here. So it might give us a shape that looks like that. And we can find the volume of that by taking slices horizontally, where the width of those slices are going to be delta y, and the radius here is going to be given by the x coordinate. So usually this is going to be a function x in terms of y. So we might have to find the inverse of the function in order to do this. But notice that in this formula here, everything's the same except we're just swapping x's with y's. In that case, this a and b here would be y coordinates, not x coordinates. So big idea: to find the volume of a solid of revolution, we're going to have cross sections that are circles. So we find areas of those circles, and that gives us our volume when we integrate that.